Usually when we evaluate how smart something is, whether it's like a student taking a standardized test or a machine running a benchmark, we really only look at the final answer.
Right. We grade the destination.
Exactly. If you imagine, I don't know, watching a maze from above, see the starting point, you see the cheese at the end. And if the subject gets to the cheese, you say they solved it. Pass or fail.
Yeah, and I mean, it's an incredibly comforting way to measure intelligence, right? Because you can just check a box, it's clean, but it completely ignores the entire journey.
It does. When you step into the world of complex, multi-step problem solving with, large language models, just checking if they found that cheese isn't really enough anymore.
No, not at all.
Because you want to know how they navigated the dead ends. Did they panic? Did they retrace their steps methodically?
Yeah.
We see these models doing what looks like step-by-step reasoning.
But then you ask the engineers why an AI can perfectly solve a complex logic puzzle one day and then completely collapse on a slightly different one the next day.
Right.
Exactly. A puzzle that is out of distribution. The diagnostic landscape just gets murky so fast.
Right. And that out-of-distribution pressure is really the true test. Welcome to the deep dive, by the way. Our mission today is to explore the absolute bleeding edge of generative AI foundations.
Yeah, for a long time, the exact architectural mechanisms that dictate whether an AI actually possesses a structural logic or whether it just spectacularly crumbles when the pattern changes, that's been a total black box.
Total black box. But today, we are opening that box for you. We're looking at a stack of state-of-the-art papers, and we're really zeroing in on this groundbreaking new preprint from researchers at McGill University and Mila, that's the Quebec AI Institute.
It's a fascinating paper. It's titled A Measure-Theoretic Analysis of Reasoning, Structural Generalization and Approximation Limits.
Which is a mouthful, but essentially, these researchers are writing the mathematical laws for AI reasoning. Okay, let's unpack this. To understand how a machine thinks, we first have to figure out how to actually measure a thought, right?
Right. And grading the final answer clearly isn't cutting it. The researchers argue we have to completely throw away our standard evaluation metrics.
Throw them away completely.
Basically, yeah. I mean, usually the industry relies on grading systems like 0-1 losses or sequence-level log likelihoods.
Okay, so if a model is trained on simple, shallow logic steps, and then you evaluate it on a deep, highly sequential reasoning task.
Standard metrics just output a fail. They don't mathematically isolate the structural reason why the fidelity of the output collapsed.
Ah, I see. So if grading the final answer is a broken methodology, we basically need a way to grade the scratch paper. We need to map the exact physical path the AI took to get to its answer.
That is the goal, yeah. But turning text into a map is it's a massive mathematical challenge.
Yeah.
To do it, the researchers used this concept called optimal transport.
Optimal transport. Okay.
Yeah, they took discrete variable length reasoning trajectories, so literally the text sequences of an AI thinking step by step, and they projected those into a continuous 12-dimensional space.
Okay, I want to pause right there and push back a little because this is where the math terminology usually loses people, including me.
Sure, yeah.
How do you map a word like therefore or a phrase like let's try another approach onto a physical coordinate in a 12-dimensional space? Like, are we just assigning a math value to every vocabulary word?
Well, no, that's the trick. They aren't mapping the semantics of the words themselves. They are extracting what they call scale-invariant features.
Okay, what did that mean?
It means they are tracking the macroscopic shape of the thought process.
The shape of the thought. That's a wild concept.
It is, but think about what happens when you solve a problem. You go down a path, you hit a dead end, you back up, maybe you try a parallel path.
Right.
The 12-dimensional space tracks those structural movements, so it tracks maximum tree depth.
Which is how far down a single line of logic the AI traveled.
Exactly. It also tracks total search volume, it measures backtracking rates, and it measures lateral shifts.
Like when the AI abandons one approach and just branches out horizontally to try something new?
Precisely. By tracking all these features, they can represent any data set of reasoning as a literal geometric shape.
Okay, so if they have the shape of one reasoning task and the shape of a different reasoning task, how do they measure the difference between the two shapes?
They use something called the Wasserstein-1 distance.
Wasserstein-1, yeah.
Yeah, in mathematics, this is sometimes called the Earth mover's distance.
The Earth mover's distance, I like that.
Yeah, it's a great visual. If you imagine your two reasoning data sets as two different piles of dirt, The Wasserstein distance is the mathematical cost and effort required to shovel the dirt from the first pile until it perfectly matches the shape of the second pile.
Oh, wow. So it gives us a strict, quantifiable cost of moving from one distribution of thought to another distribution of thought.
Exactly.
Okay, I follow the mapping process now, but I still have this lingering concern about just, throwing away the actual words.
You're worried about the semantics.
Yeah. By projecting complex natural language text into just structural dimensions like depth, backtracking, branching, aren't we losing a ton of semantic nuance?
You would definitely think so, but the researchers address that concern directly. They use what they term the epsilon relaxed structural sufficiency assumption.
Epsilon relaxed structural sufficiency. That sounds incredibly dense. Let's break that down.
Right, so informal combinatorial planning, so things like algorithmic search tasks, complex math, or logic puzzles outcome correctness, is strictly dominated by macroscopic structural routing.
Meaning, did the AI navigate deep enough? Did it successfully backtrack when it hit a wall?
Yes, because if the AI takes the wrong branch in a logical search tree, the specific isolated token semantics simply do not matter. The epsilon in that formula just accounts for the tiny microscopic residual error of the exact words used.
Oh, I get it. Because if you take a wrong turn in a maze, it really doesn't matter how beautifully you describe the wall you just walked into. You're still at a dead end.
That's a perfect way to put it. The structural logic is what guarantees the solution, not the associative pattern matching of the text.
This shifts the entire paradigm for me.
Yeah.
It proves that true AI reasoning isn't just like a fancy autocomplete stringing together words that sound plausible.
No, it's an engine actively navigating a highly specific physical geometry of thought.
Which brings up an immediate logistical problem in my mind. If I'm navigating a complex city grid, I need to know my current location. How does an AI architecture actually track its own position on this 12-dimensional map while it's generating text?
And that tracking mechanism leads us directly to the first major architectural law discovered in the paper. It comes down to positional encodings.
Positional encoding, so how the AI tags the order of its own thoughts.
Exactly. And we generally see two approaches to this in the industry. There's absolute positional encoding, which is known as APE, and rotary position embedding, or ROPE.
Okay, let's use a navigation analogy for you listening. Using APE is like memorizing a strict sequence of absolute street addresses.
Right.
You are at 101 Main Street. Your next thought is at 102 Main Street. The next is 103. But using ROPE, on the other hand, is like holding a compass that only gives you relative directions.
Yes. It doesn't care about the street address at all. It just says, from wherever you are right now, go 2 blocks forward.
So an absolute address versus a relative compass.
And that distinction turns out to be the exact dividing line between an AI succeeding or suffering a total representational collapse. The researchers outline this mathematical vulnerability they call the Lipschitz gap.
Lipschitz gap. I'm guessing this is what happens when the absolute street addresses get messed up.
Exactly. When an AI uses APE, those absolute coordinates, and you shift a reasoning subtrajectory even slightly, you disrupt its entire coordinate system.
Okay, give me an example.
Let's say the AI is halfway through solving a math problem, realizes it needs to insert an intermediate thought, and generates a few extra tokens.
Oh, I see where this is going. If it inserts a new thought at 102 Main Street, then the thought that was supposed to be at 103 gets bumped to 104. Everything downstream gets a new absolute address.
And the cascade effect is immediate. The paper proves that under this coordinate disruption, the local attention kernel of the AI diverges.
The attention kernel, meaning the part of the math trying to weigh the importance of different words against each other.
Right. The math literally fails to cancel out the position changes. This triggers a cascading error that guarantees the model's expected risk will just skyrocket when it faces out-of-distribution data. The model loses its place on the map, and the reasoning collapses.
Wow. This is incredibly illuminating for anyone who uses these tools daily. Like when you ask an AI a complex, multi-step question, and it's doing great for 3 paragraphs, but suddenly it just completely loses the plot and starts hallucinating absolute nonsense.
Yep. You are likely witnessing a coordinate disruption in real time.
It inserted a thought, the absolute coordinates shifted, the attention kernel diverged, and the AI effectively forgot where it was.
But what's fascinating here is that if the AI uses rope, your compass analogy, it acts as a continuous structural regularizer. Because ROPE measures relative distances, it preserves what we call sequence equivariance.
Sequence equivariance. meaning the local relationships stay the same, regardless of the global position.
Exactly. The math proves that ROPE maintains the local dependency structure. So if the problem structure shifts, or the AI inserts a really long tangent, the relative distance between the key concepts remains stable.
It still knows how to go 2 blocks forward relative to its current thought.
Right. It averts the collapse.
Okay, so swapping the GPS for a compass prevents coordinate disruption, but knowing where you are on the map is really only half the battle. Your brain still has to be able to process the complexity of the route itself.
That's true.
What happens when the AI actually has to do the heavy lifting of backtracking, like when it hits a dead end, realizes a mistake, and has to hold a complex thought in its memory while it unwinds its previous steps?
Now you're touching on the fundamental algorithmic bottleneck of modern AI, and it's actually the second massive finding in this paper. It revolves around two computational complexity classes known as TC0 and NC1.
Okay, TC0 and NC1, let's translate those complexity classes into how an AI actually processes a problem.
Think about what recursive backtracking requires. In computer science, it's essentially a deck language.
A deck language.
Yeah, which is a formal way of describing balanced parenthesis matching.
Oh, right. Like, imagine a long algebra equation with multiple nested parentheses. To solve it, you can't just read left to right. You have to find the innermost opening parenthesis, park the outer equation in your working memory, solve the intersection, match it to its closing parenthesis.
And then retrieve the outer equation to keep working your way out.
Exactly. That perfectly balanced nested matching process belongs to the computational complexity class NC1.
The problem is that a standard transformer AI model, which, by the way, is the architecture powering almost all modern language models, operates with bounded numerical precision and processes things in parallel layers.
Right.
Because of this architecture, the transformer is strictly limited to the complexity class TC0.
Wait, really? So the AI is fundamentally a TC0 machine, but we are asking it to solve an NC1 nested parenthesis problem.
Yes.
That sounds like a strict physical limitation, not just a software bug that could be patched.
It is a physical limit. A constant depth TC0 circuit simply cannot evaluate arbitrary NC1 functions. The researchers proved that if you try to scale the AI's power simply by making its representation wider, increasing its hidden width, which engineers denote as the variable emit inherently plateaus.
Okay, here's where it gets really interesting. Let's use a restaurant kitchen analogy to understand width versus depth. Making a neural network wider is like adding more horizontal counter space in a commercial kitchen.
I like that.
If you need to chop 50 onions at once, wide counter space is fantastic. You can do many simple prep tasks in parallel. The paper calls these shallow lateral state expansions, right?
Exactly. But recursive backtracking, that nested parenthesis problem, requires a last and first out stack. Chopping 50 onions simultaneously won't help you remember the exact sequence of a complex multi-course order where the customer keeps changing their mind.
Right. And you have to undo specific modifications in reverse order. For that, you don't need more horizontal counter space. You need physical depth. You need that sharp metal ticket spike on the counter.
The ticket spike.
You stab the order tickets onto the spike one by one so you can pull them off in the exact reverse order later. What the researchers are saying is that you must scale the physical layer depth of the neural network, the L variable, to overcome this bottleneck.
And if we connect this to the bigger picture, it establishes a definitive deep is better law for search reasoning. You cannot bypass the need for physical depth just by throwing more parameters at a wide layer.
You just can't.
The researchers prove this by showing the model hits irreducible approximation bounds in what are called barren spaces. In functional terms, the efficiency of widening the network eventually flatlines completely.
So if you want the AI to successfully parse deep, nested backtracking without hallucinating, it must have deep physical layers to execute those sequential reductions.
Exactly.
Now, theory and mathematical proofs are incredible, but they need to survive contact with reality.
Right.
How do the researchers actually test these strict bounds? Because asserting a fundamental law of AI architecture requires a lot of empirical receipts.
Oh, they brought the receipts. They built an incredibly rigorous proving ground. They evaluated 54 distinct transformer configurations.
54?
Yeah. They tested across small, medium, and large parameter scales. They varied the aspect ratios, building deep models, wide models, and balanced models, and then they crossed all of those variations with both APE and ROPE positional encodings.
Wow, so 54 custom models built from the ground up just to test the math. What was the actual task they made them perform?
They used a combinatorial planning task called the countdown game. And they ran it through a framework called Stream of Search, or SOS.
Stream of search?
Yeah, this framework allowed them to strictly synthesize and control the target distributions of the problems. They really wanted to force the models to handle extreme coordinate shifts.
How do you force a coordinate shift in a controlled way like that?
By manipulating the types of search the model has to perform. So they trained the models on shallow lateral searches known as breadth-first search, or BFS.
Okay, this is where you explore all immediate options before moving deeper.
Right. But then during testing, they hit the models with a brutal 50-50 mixed distribution. Half shallow BFS and half deep recursive backtracking searches.
Depth first search, DFS, where the model has to dive all the way down a rabbit hole and then back its way out.
Exactly.
So they basically trained them to swim in the shallow end and then threw them into the deep end with a weight tied to their ankle.
Pretty much.
Yeah.
And the empirical results were striking. Let's look at the large wide model using APE. This is a model with a massive number of parameters, but it's built horizontally wide instead of vertically deep, and it relies on absolute street addresses for its position.
Right.
When it hit that mixed testing distribution, it suffered a massive representation collapse. It scored a dismal 42.15% accuracy.
A 42% on a logic test. I mean, it basically lost the ability to reason.
It did. But then they took that exact same scale model, the exact same parameter count and wide aspect ratio, and simply swapped out the APE coordinates for the ρPE compass.
So they just gave it relative sequence equivariance?
Yes.
The model still lacked depth, but at least it had relative tracking. How much did that compass help?
The model recovered over 12% absolute accuracy, jumping up to 54.25%. Just changing how the architecture tracked its position allowed it to bypass the coordinate disruption entirely.
That is amazing. That perfectly proves the ρP theory. But what about the deep is better law? Did the deep models actually outperform the wide ones as the TC0 versus NC1 complexity math predicted?
They didn't just outperform them. The empirical accuracy of every single model tested perfectly mapped to the theoretical upper bound ceilings derived in their math.
Wait, perfectly mapped?
Perfectly. Every data point in that 54 model grid sat exactly where the equations predicted. No magnitude of horizontal width scaling could push a model past the depth limit. The irreducible bounds were totally real.
So what does this all mean? If we zoom out and look at the entire landscape of artificial intelligence right now, what is the ultimate takeaway from these experiments? It seems to fundamentally challenge how some developers are building models today.
The overarching takeaway is that an AI's architecture is not just a passive container for data. It is a strict physical constraint on the model's logic. This data empirically confirms that ρPE isn't just a convenient tool for handling larger context windows and longer text inputs, which is, frankly, how much of the industry treats it. It actually operates as a fundamental continuous structural regularizer. And more critically, if you want an AI to truly reason through complex problems, to hit dead ends, hold a thought, and successfully backtrack, you must prioritize depth over width. Aspect ratio dictates performance.
Wow. Let's briefly recap the journey we just took, because we covered a lot of ground today. We started with the mystery of out-of-distribution reasoning failures.
Yep.
To solve it, we translated abstract thought processes into a 12-dimensional continuous space, tracking the exact geometry of problem-solving, the branching, the depth, the backtracking. We explored why relative tracking, the ρP compass, prevents an AI from getting mathematically lost when its coordinate system shifts.
And finally, we established the definitive deep is better law, demonstrating that wide networks will always plateau against the TC0 complexity bottleneck, while deep networks provide the structural spikes necessary to resolve nested backtracking logic.
And we should really emphasize to you listening that these aren't just academic musings confined to a research lab.
Not at all. As the tech industry pivots aggressively toward search-based LLMs and inference time scaling,
Which basically means giving the AI more time to think and search before it outputs an answer.
exactly. As we move toward that, these mathematical boundaries become the blueprint. These are the actual laws dictating the structural integrity of the next generation of AI that will be sitting on your laptop or your phone.
Which brings up a really compelling question, something inspired directly by the author's own limitations in future work section.
Yeah, this is where it gets really sci-fi. We've just mapped out the strict physical limits of a single autoregressive forward pass. We know what a model's architecture allows it to do on its own in one continuous stream of thought. But what happens when we introduce advanced inference time interventions?
Interventions from outside the model itself.
Think about techniques like tree of thoughts or Monte Carlo tree search. These are frameworks where an external algorithm actively guides the AI during the generation process. It prompts it to branch out, forces it to evaluate different paths, and aggressively prunes bad ideas in real time.
Okay.
If the AI is naturally navigating that 12-dimensional topological map we discussed, how do these dynamic real-time external interventions reshape the target measure while the AI is actively thinking?
That is a wild concept. Are we just dragging the AI across its existing map, or are these external algorithms actively terraforming the mathematical landscape of thought in real time to create a safer path?
That is exactly the next frontier of this research, understanding how inference timescaling literally alters the geometric cost of reasoning.
Terraforming the landscape of logic while the machine is actively trying to navigate it. We started the deep dive by talking about looking down at a maze from above, just waiting to see if the subject stumbles onto the cheese. By applying these measure-theoretic analyses, we are finally down in the maze with them. We're measuring the walls, tracking the footprints, and watching the architecture of artificial thought unfold in real time. Next time you ask an AI to solve a complex, multi-step problem, take a second to ponder that invisible 12-dimensional map it's navigating and whether its neural architecture has the physical depth to find its way back out of a dead end. Thanks for joining us on this deep dive.